Okay, in this class, we will be concluding the recursive least squares adaptive filter, RLS, that is recursive least squares adaptive filter. We have already done the derivation, discussed at length. Just a few issues, couple of issues are left. One is that if you recall, we had the data matrix at nth point of time . So, filter has p plus 1 coefficients, that is why p plus 1 columns. So, this vector we wrote as x n transpose, and this part was just we have seen x n minus 1, this part. So, it is basically x n minus 1 and x transpose n. And then we found out that least squares estimate of the filter coefficient vector at nth clock, that is using data from n equal to 0 from time from clock from 0, index 0 to index n, that was this x n transpose lambda n x n inverse x n transpose lambda n d n. D n is the real response vector, and lambda n was this where lambda forgetting factor. And here we assumed that this matrix, we call it A n, this is invertible, and that is where the problem is, invertible. And under that assumption, in fact, we related, these are all results which have been derived in the previous lectures. So, we will not redo them, only recall them. Then A n was related to same matrix, but at n minus 1th clock, like this. And then assuming that both A n and A n minus 1 are invertible, we use the matrix inversion lemma, so that A n in so that we use matrix inversion lemma, so that A n inverse and A n minus 1 inverse, they get related through some expression. That is, we express A n inverse in terms of A n minus 1 inverse, and then proceed, derive something called gain vector and all those things, algorithm is derived. But this assumption that they are invertible, that has to be enforced, because you can see, as we discussed earlier, here number of columns is p plus 1, number of rows as such is n plus 1. If n is less than p, then we have number of rows less than number of column, and we have seen earlier, we have seen that in such cases this matrix, which is Hermitian, A n is Hermitian, but it is not positive definite, and therefore it is not invertible. That we have seen at length, and this will happen because n has to start from 0, then 1, then 2, then 3, then only it will go. So, in the initial stages, number of rows will be less than number of columns, and so this formulation will not work. So, what to do then? How to make sure that the invertibility issue does not bother us? So, for that, what we do, consider this expression. Here, we again write A n minus 1. So, we write like this. First, write what we have written there. Then this we replace again by the same expression, replacing n by n minus 1 in the left hand side. So, then we get A n minus 2 okay. So, this becomes this entire thing, A n minus 1 by the same formula. If you replace a n by a n minus 1 in the left hand side, you get lambda a n minus 2 plus x n minus 1 x n minus 1 transpose. That is what you replace. This lambda is this lambda and good old x n x transpose n. Again you replace a n minus 2 by the formula, it will be lambda a n minus 3 plus x n minus 2 x n minus 2 transpose. Replace that here and go on doing it. So, if you do that, you will finally get lambda to the power n x0 transpose. Okay, let me write it in the next page. It will be like this. Lambda to the power, so I go back by n plus 1 steps. So, it will be a minus 1. See this. When I have lambda to the power 1, a minus 1. When I have lambda to the power 2, a n minus 2. So, when I have a 0, lambda to the power n. When I have a minus 1, lambda to the power n plus 1. Okay. That is why lambda to the power n plus 1, a minus 1, and then you start like this. Okay. Now, this is 0 because our business starts from n equal to 0. Previous to that, whatever data I have, that all that is 0. So, this is 0. So, actually we have this. Now, this is a Hermitian matrix. We have already seen A n is a Hermitian matrix. Now, here you can see this is Hermitian because any vector, column vector into its transpose, it is Hermitian. You can, if you take the transpose, here all are real, so no conjugation. So, only ordinary transpose is same as Hermitian transpose. So, if you take the transpose of this, you get back A transpose. So, this is Hermitian, this is Hermitian, this is Hermitian, and summation of Hermitian matrices is Hermitian. For instance, if A and B are Hermitian, then A plus B also Hermitian, because we know A plus B H means what? First A plus B transpose, then conjugate, or vice versa. When you sum the two matrices and they transpose, you will get the same thing if you first take transpose of both and then add and then star. So, if you add any I comma jth element of this A transpose with the I comma jth element of B transpose and then conjugate, it is same as if you first conjugate the I comma jth element of A transpose and I comma jth element of B transpose and then add. Okay. So, it will be A transpose star plus B transpose star, which means AH plus BH. Very silly thing, very simple thing. So, now this every component is a Hermitian matrix. So, this is Hermitian. Alright, since it is Hermitian, we can write it in this form T D T H, where T is unitary, T T H is T H T is identity. What is this? It consists of mutually orthonormal eigenvectors of this total Hermitian matrix placed side by side, and D diagonal matrix consisting of the eigenvalues of this Hermitian matrix, all are real. Now, since in the early stage of the algorithm, as I said, this is not positive definite and therefore, it is not invertible. That means determinant is 0, then only a determinant of this matrix is nothing but product of the eigenvalues we have seen earlier in the early part of this lecture series. Okay. Determinant to the entire thing is nothing but determinant of this diagonal matrix, which is product of the eigenvalues. So, if the matrix is not invertible, in the early stage of the algorithm that at least one eigenvalue should be 0, then only determinant is 0, and that is what we will try to avoid. What we will do, we will take this summation and add with this as we take this initial value for this A minus 1. Okay. What? A diagonal matrix where delta is real and very, very small, positive, very, very small. So, then that is we can write as delta ID. So, therefore, A n will not be just this, it will be delta I plus this T d T h, whatever I got here, and then I can write as T because this is unitary. So, T identity T h, identity into T h is T h, which is identity matrix, and T T h is I. So, delta I and T d T h as before. So, take T common and T h common, delta I plus D, which means I have got lambda 0 plus delta, lambda 1 plus delta dot dot dot, lambda n plus delta. So, all the eigenvalues, this is a positive semi-definite matrix. So, they are either 0 or positive, but since it is not invertible, at least there is one 0. But now everybody getting added by some small positive number. So, now nobody is 0. Therefore, determinant will be positive, okay, and it is invertible. So, this is that initial value, instead of ideally 0, I take it to be delta I, where delta is very, very small. So, it does not create any error, much error in the program, in the algorithm, because ideally this should have been 0, but still I keep it as a positive constant delta times I, and so this matrix invertibility issue is resolved. So, this is one issue I had to discuss, and now I write the algorithm. One thing you remember, by the way, A n minus, or okay, maybe I will do it little later. Let me formulate the algorithm. Initialize A minus 1 as delta I, as I said. I need W minus 1 also in that priori error calculation, take it to be 0. Then first step is gain vector Gn computation. Okay. Now, what was Gn? Gn was lambda inverse let me check, xn divided by 1 plus lambda inverse x transpose n, okay, which is nothing but lambda, and I call this to be, suppose this A n minus 1 inverse is given to me, okay, like A minus 1 is given. So, A minus 1 inverse is nothing but 1 by delta times I. So, this is given to me. Okay. Let me call it, since this is assume this to be given, let me call it UN. So, I will calculate it once, because here in the denominator also this factor comes. So, why calculate twice and waste computational resource? So, calculate is only once for the numerator and use it in computing the denominator. And also lambda inverse, if you multiply numerator and denominator by lambda, so you have got lambda cancelling out, there is lambda plus this thing. So, you calculate UN as I told you, we are starting at n equal to 0 to final. Final can be any point of your choice. Let me write it more clearly. To some point set n equal to 0, this inverse is with us because A minus 1 inverse, if I know A minus 1 and all the diagonal entries are positive, so A minus 1 inverse is nothing but 1 by delta times I. So, this I call UN. Using this UN, I write Gn as, so I am assuming this to be known, A n minus 1 inverse given at the nth stage. So, therefore, when I go for the n plus 1 stage, I will have to make sure that A n inverse is also available, okay, and that is how we will proceed. So, Gn is UN vector divided by a scalar number, and scalar number is lambda plus x transpose n UN. This part is UN, so x transpose n UN. All right. Then number 2. Computation of the a priori. By the way, or okay, maybe I was computation of the a priori error E n minus 1 n. So, for that, we remember we find out this output where we use the current data vector, but filter coefficient vector we use, which is obtained by taking data up to the previous clock, up to n minus 1th. Okay. So, that was, so I am at the nth clock, I am still using the current data vector only, but using the filter vector of the previous index. Okay. And then this error is nothing but current desired response minus this output. Number 3, adaptation of the weight vector. Simply we derive the formula, it was from W n minus 1 plus G n Number 4, now this is the correct weight vector. So, filtering, this is a common FIR filtering y n, that is I got the filter weight vector for the current cycle. So, I just use it to filter the current data vector and get the output. Okay, this is my actual, this is a conventional style, conventional filter output. This is what we will take and filter output. This was previously y n minus 1 n was just to compute this a priori error. But now, last stage is very important, and that is updating inverse matrix. That is, I assumed that at nth clock A n minus 1 inverse is available. Therefore, when I move to the next clock A n plus 1, that time I should make sure A n inverse is available. But we had already obtained the formula A n inverse. What was that? A n inverse was lambda inverse A n minus 1 inverse minus lambda inverse G n x transpose n A n minus 1 inverse, right. This is what? Take lambda inverse common. So, this is known to us A n minus 1 inverse G n. Now, this quantity x transpose n a n minus 1 inverse. Okay. We have seen a n minus 1, here we have seen inverse x n is u n. So, what is u transpose n? X transpose n a n minus 1 inverse transpose. Now, remember a n minus 1 is Hermitian, and we had proved early part in of this lecture series that if a matrix is Hermitian, its inverse also is Hermitian, assuming inverse exists. Inverse also Hermitian. So, therefore, its transpose is itself. So, it will be x transpose n inverse, and that is what I have here, x transpose n a n minus inverse. So, it is g n into u transpose n. End. So, that is the end of this algorithm, and also that marks the end of this course. I hope through this course I could impart sufficient knowledge starting from probability, random variable, properties of correlation matrices, Hermitian form, positive definite form, optimal filtering, adaptive filtering, and a lot of derivations which are useful in many other contexts and applications of adaptive filters. And these are not only used in the context of adaptive filter. Adaptive filter was a pretext, was a tool around which I could develop this theory. Okay, but all these are very useful in several other areas like communications, for that matter, wireless communications, image processing, video processing, neural networks, deep learning, and all that. So, I am sure you will be able to use this knowledge. If you do not forget, you will be able to use this knowledge in many other contexts as well. So, on that hope, I wish you all the best. I conclude my lectures here. Thank you very much.